Welcome to chapter 22. This chapter starts us into magnetism. So to begin with, we'll want to look at magnetic fields around simple bar magnets. This photograph shows you what little bits of iron filings would look like if we had two bar magnets, but they were oriented so that they had it says with opposite poles adjacent. These are actually like poles. It shouldn't say opposite. It should say, this is like. I'm not sure why. It had a typo. So these are like poles. Like poles repel each other. With magnetism, it follows some of the rules that we're used to with electric charges. Magnetism is bipolar. So we have a north pole and a south pole. Like poles repel, opposites attract. And so you can see in this drawing how the magnetic field lines are repelling each other. And that means that they are opposite. Maybe the one on the left is the north magnetic pole, and the one on the right would be the north magnetic pole, or maybe they're both south magnetic poles. But like poles repel. And so you can see that the magnetic field lines come and then they push away in the very center. So, like I said, magnetism is bipolar, a north and a south. And unlike electric charges, with electric charges, you can have an isolated electron or an isolated proton. With magnetic fields, you cannot have an isolated north magnetic pole or an isolated south magnetic pole. So now that we've fixed that typo, let's look at this second one. Aha, my captions were just opposite from each other. All right, so on this one, you can see that the magnetic field lines attract each other. And so that means that they have to be opposite magnetic poles. So maybe the one on the left is north and the one on the right is south, or vice versa. So opposites attract, likes repel. This second photograph is showing the magnetic field lines going across, so they're attracting each other. So please correct the two mistakes. All righty, so as I've said, the north magnetic pole is on a bar magnet, and we'll talk about that. It got its name because the north magnetic pole is the pole that will freely point towards geographic north if you suspended the bar magnet. So if you had a bar magnet and you tied a string around the middle and just held it, it would spin until it was oriented that the north pole on the bar magnet pointed towards geographic north. Sometimes they would refer to it as a north-seeking pole. Now, so here's our little drawing of the bar magnet suspended by a string. You can see that the north pole on the bar magnet is pointing towards the geographic north pole. What that means is that since we know opposite magnetic poles attract, that means the north pole on the bar magnet must be attracted to a south magnetic pole. And it's as if in the center of the earth, there's this giant bar magnet where the south magnetic pole is in the northern hemisphere and the north magnetic pole is in the southern hemisphere. This is actually an older drawing. If we were doing our little bar magnet, it's not oriented this way anymore. Instead of pointing off to the left of the screen, it now points slightly to the right. And we'll talk about that in a few minutes. So let's look at some things that are magnetic. So there's some materials that are naturally magnetic. We refer to those as ferromagnetic materials. Some ferromagnetic atoms are iron or cobalt, nickel, and gadolinium. Those are all have naturally magnetic properties associated with them. with charge, if you got charge down as small as you could get it, you'd have a proton or an electron. With magnetism, when you get it down as small as you can make it, what you have are magnetic domains. These are the smallest portions of matter with magnetic properties. So if you subdivide it, you lose the magnetic properties. So a magnetic domain is as small as you can get and maintain the magnetic nature of the material. And as you can see, they go from 10 to the minus fourth centimeters down to a tenth of a centimeter, and that's just a millimeter. So a pencil line is about as small as you can get. If you have a piece of iron, it might be unmagnetized at the moment. You can't use it to pick up paper clips or pins. In that case, the magnetic domains would be randomly oriented. So in this first drawing, we have our little arrows representing the magnetic domains, and they're pointing a variety of different directions. In the second drawing, you can see that the magnetic domains, symbolized by these arrows, are all pointing a single direction. They've been organized, lined up. And what that means is we've taken our ferromagnetic material, and by organizing these magnetic domains, we have turned it into a magnet. We say magnetic field lines go from north to south. So the arrowhead always points towards the south magnetic pole, and the opposite end of the arrow is the north magnetic pole. So how do we organize those magnetic domains? Well, you can organize or disorganize magnetic domains by using a strong outside magnetic field. If you took a sewing needle and you put it on a bar magnet and came back in a week, the magnetic domains in the sewing needle would have aligned themselves in such a way that the needle is now magnetic. So a strong outside magnetic field can change the magnetic orientation of the domains. You can organize it in the sense of the sewing needle, or if you had a magnet and you put it in the wrong orientation next to a strong second magnet, you could screw up your first magnet and make it the domains disorganized and mess up its magnetic field. You can also do this with a physical shock. So you don't want to drop a bar magnet repeatedly. Repeatedly dropping a bar magnet jars the atoms and gives them enough kinetic energy that sometimes they reorient. And you can do it with the thermal shock. If you heat a material that has magnetic domains just a little bit, you give the magnetic domains more kinetic energy and they tend to self-align and make the material more magnetic. Conversely, you can overheat it and give them too much kinetic energy and they just go crazy and you don't have magnetic domains organized anymore. So what is that magic temperature that screws things up? That is the Curie temperature. The Curie temperature is the temperature which your domains are so disorganized that you can't have a magnet. For iron, the Curie temperature is 770 degrees Celsius. So that is very, very hot. I think under normal conditions, we're safe. We believe that all magnetism is a result of the spin on the electron. Now, please remember when we talk about spin, we don't think that they're twirling like a merry-go-round. It's just a way to describe something that produces two states. We refer to the spin as being spin up or spin down. I know you thought I was going to say clockwise and counterclockwise, but we talk about spin up and spin down. And it's just an intrinsic property of electrons that they have this property that we call spin, just a name. So the magnetic field lines point in the direction that a compass needle would point when placed at that location. So if this is our bar magnet with north on the right and south on the left, if you put a compass right here on the very top outside line, the compass needle would point to the left. If we brought it down parallel to that location, it would continue to point to the left. If we came to the opposite side of it, it would continue to point to the left. But if we came to the end of the right end of our bar magnet, it would go straight to the right. Or if we came to the left end, it would go also straight to the right. And we'll do this. We won't map out all of the locations, but we'll look at some of them in lab. So you should notice that the magnetic field lines, which is what these drawing indicates, are closest together when you're close to the bar magnet, and as you move out, they spread out. So field lines are strongest close to the magnet and weakest as you move away. The magnetic field strength is a vector, so it does have direction. Again, we've said it goes from north to south. And it would be defined in terms of the torque. Now remember, torque is the rotational equivalent of force. So it's the torque exerted on a compass needle when it's not aligned with the magnetic field. So when you first bring a compass in and set it down, the needle will turn so that it orients with the magnetic field. And how quickly it does that is a measure of the strength of the magnetic field at that location. The closer you are to it, the faster it's going to reorient. The farther away you are, the slower this is going to be. We could do a lab where we actually plotted all of these. This is a lab. In fact, we used to do one like this, where you have a bar magnet on a piece of paper and you take these little bitty compasses and you put them around and you trace the direction that the compass needle is pointing as you move around the bar magnet. We will not do this. So in physics, B is the magnetic field strength, capital B. Another name for that would be the magnetic flux density or the magnetic induction. We oftentimes just call it the B field, but you need to know that B is for the magnetic field. I have no idea where that comes from. So why does the Earth have a magnetic field? Well, it has a magnetic field because it has ferromagnetic materials at its core. Deep inside the Earth, there is a tremendous amount of iron. And this iron is so hot that it is molten, it moves around, and it's allowed to reorient in such a way that we have a magnetic field. We've already said that the north pole of a bar magnet is always going to point to geographic north. And we already said that opposite poles attract, so that must mean that somewhere in the northern hemisphere is the south magnetic pole of the Earth. It used to be in Canada. The magnetic pole in the northern hemisphere used to be in Canada. It has already left Canada and is headed towards Siberia. So it's gone from Canada up to parallel to the geographic North Pole, and now it's actually on the other side of it, heading in the southerly direction towards Siberia. There are about 250 miles between the magnetic pole in the northern hemisphere and the geographic pole in the northern hemisphere, and it is continually changing. Here's a little graphic. It was published in Nature magazine, and you can see that back. Okay, so here's Canada. You've got to realize the little black dot right here, I guess it's more gray, is the North Geographic Pole. So we're looking down on the planet. This is Canada over here on the left-hand side. If we were looking for the US, it would be below Canada, so way over here. This is the island of Greenland. Remember, Greenland is the largest island between North America and Europe. And if we go across, so here's the geographic North Pole. That means way over here on the right side is Siberia. So in 1900 and 1910 and 1920, these first three dots give its location. 1930, 1940, you can see that's 1960. Here's 1980, 1990. Whoa, between 1980 and the year 2000, the poles began to move rather quickly. And from 2000 to 2010, look at the jump. From 2010, normally you can see that they only readjust every 10 years, but there was such a change between 2000 and 2010 that they kept better tabs on it. And at 2015, it was this location. At 2020, it had actually gone past the geographic North Pole. And like I said, is heading south into Siberia. So a very dynamic polar situation. Does it matter for most of us? No, but it matters if you have to keep up with GPS. So the Earth's magnetic field is perpendicular to the surface at the poles, and it's parallel or almost parallel at the equator. And anywhere between the poles and the equator, it goes between 0 and 90 degrees. Why does that matter? Well, at the poles, there's a little magnetic window, and that lets charged particles from deep space enter the Earth's atmosphere. These charged particles are called cosmic rays. They enter the Earth's atmosphere, and they're the reason we have the aurora borealis or the northern lights, and it's the reason there are the southern lights in the southern hemisphere, because of that magnetic window in the polar region. So the charged particles from deep space enter the Earth's atmosphere, and depending on the gases that these charged particles encounter, it energizes them so much that they knock the electrons out of place. When the electrons fall back down into their locations, the energy is given off in the form of visible light, and the color of the light depends on the gas you're energizing. You may have remembered from our very first lab where we had the tubes trying to figure out what gas was in the plasma globe. And different tubes created different colors. Well, that's because of the different gases. The aurora has different colors because of the different gases. So the magnetic dip is the angle between the Earth's magnetic field and the horizon. We're actually not going to use that, but it is important for you to know what magnetic declination is. That's the difference between, excuse me, the magnetic and the geographic pole. So it's between what your compass says is north and what in reality is north. So if you had a compass and it lined up, it's going to line up with the magnetic direction. And I know this says magnetic north. It's actually the compass needle itself is a little bar magnet, and the North Pole on it points in this direction. So this is really a magnetic south pole up here. Geographic north is where the pole that the axis of the Earth has and that the Earth rotates around. So depending on where you are, this is a big difference or a little difference. If you are closer to the equator, it's not such a big difference. But the closer you get to the poles, the bigger you're going to be off, the bigger your mistake. So if you use a compass to locate which way to travel, sometimes it produces an accurate result, sometimes it doesn't. GPS is continually being reoriented based on what is the Earth's magnetic pole. So this diagram shows you the magnetic field declination for 2010. The black line you see would be the one that if you used your compass, it would actually point you in the correct direction. And so you can see that if you're on one side of it, you have to deduct 20 degrees or 10 or 5 or whatever. And if you're on the other side, you have to add. So it's going to change. Do you swing right or do you swing left? And you can see it depends on where are you on the planet as to which way you have to make your corrections. This one was for 2010. This is one of the United States in 2004. It's, I'm sure, not accurate anymore because the magnetic field has changed quite a bit since 2004. So it has shifted. But you can see this is the zero declination line, so the line where you wouldn't have to correct at all. Back in 2004. So how about that changing magnetic field? Well, we've talked about how it's moving rapidly towards Siberia right about now. It has actually undergone field reversal at least 20 times in the last 5 million years. We expect another field reversal in about 2,000 years, but it could happen sooner. Who knows? We know about these field reversals. Now, a field reversal is when the North and the South poles swap locations. And again, we're talking about magnetic poles. The geographic one stays fixed. But the magnetic poles have actually reversed. How do we know this? We know it by looking at the way the magnetic material in igneous rocks is located. So when igneous material solidifies, it's molten material, anything in it that's ferromagnetic will orient itself with the Earth's magnetic field at that location. And when the rock solidifies, those magnetic domains are more or less permanent in that location. And so over time, geologists have been able to map these magnetic field domains in rocks and have come up with some very interesting information. One was that the large parts of the Earth's surface called tectonic plates have actually moved over time. And another is that the North and South magnetic poles have actually flipped. So it's all information trapped in those igneous rocks that leads us to this information. Let's talk about electric currents and how they can produce magnetism. So we have Hans Christian Ørsted to thank for some of this. He discovered that a moving electric charge is associated with a magnetic field. He connected a wire to a battery, and when the battery was turned on, a compass needle near it moved, and when it was turned off, it flipped back the way it was before. So if you have a current flowing through a wire, there is actually a magnetic field surrounding the wire. The magnetic field circles the wire. And we will need to use what's called the right-hand rule. We'll talk about this in class, but we'll use the right-hand rule. So on the right-hand rule, your thumb, and you can see in the drawing, here's a little thumb. The thumb points in the direction of positive current. Now, in reality, we believe it's the electrons that do the moving, but humor me. So if we have the direction of positive current, that's your thumb, then the fingers on your right hand would curl in the direction of the magnetic field around the wire. And so you can see if we have a piece of wire going from the bottom of the page to the top of the page, bottom of the page to the top of the page, then and the positive current is pointing to the top of the page, then the fingers on your right hand would curl so that they come out of the page on the left, parallel in front, and go back into the page on the right hand side. So they circle around the wire. We'll do this in class. Everybody will use their right hand. We'll practice it. So what are some of the forces on an electric current and a magnetic field? Well, again, we would use the right-hand rule. So if your thumb points in the direction of positive current, your fingers are going to point in the direction of, in this case, an outside magnetic field, an outside B field. Then the palm of your hand is going to face in the direction that your current in the wires or your charge is going to be forced. So again, it's a right hand. The thumb is the direction of positive current. The fingers are that outside magnetic field. And the palm of the hand is the direction that the charge or the current carrying wire will be forced. And again, we'll deal with this in class. I think it's much easier if we work with it in class. To find the magnitude of the force on your current, we use our first equation for the chapter that we have to keep up with, and it's F equals Bill sine theta. F equals B I L sine theta. F is the force measured in newtons. B is the external magnetic field measured in Teslas. I is the current in the wire, and current is measured in amps. Capital L is the length of the wire that's in that magnetic field. It would be measured in meters. And theta is the angle between your wire and the magnetic field. And you will need to know this equation for the quiz. So we measure the external magnetic fields measured in Teslas, just like we have meters for length. We also could use centimeters if we're doing CGS units. Remember, CGS stands for centimeters, grams, seconds. The B field in CGS units is measured in Gauss. And the only reason I mention that is because people talk about the magnetic field at the surface of the Earth being roughly a half a Gauss. So you can see a Gauss is pretty small. A strong electromagnet can produce fields that are, say, 2 Teslas or more. Superconducting magnets, you can get more than 10 Teslas out of them. Sometimes we keep trying to find non-invasive ways to heal people and to image and to do all kinds of medical procedures. And so we are looking at using magnetic fields for all kinds of treatments. It's an ongoing process and continues to change. So let's look at the force on an electric charge moving in a magnetic field. So remember before we had F equals BIL sine theta, where I was the current and L was the length of the wire. Suppose you don't have a wire. Suppose we just have a little zippy electron out there moving around. Well, F equals QVB sine theta, where capital F is the force in newtons, little q is our charge in coulombs, little v, not capital, but lowercase v, is the velocity of the charge. How fast is it going? Capital B is that external magnetic field measured in Teslas, and theta is again the angle between the velocity vector, remember velocity has a direction, and the magnetic field. Suppose we don't have positive charges. Suppose we could have negative charges. Well, you can still use the right-hand rule, but you just switch the direction your thumb is moving in. So if you have a positive charge going to the right, you would point your thumb to the left, because the right-hand rule is, I'm sorry, I said it backwards. If you have a negative charge going to the right, you point your thumb left, because remember the right-hand rule is for positive charge. And again, we'll do this in class. We also have a few examples. We'll see how well they go. All right, so when we do our drawings, if we have current going into the paper or out of the paper, we symbolize it as either a dot or an X. We symbolize it as either a dot or an X if it goes into the paper or out of the paper. If it goes to the right, it's just an arrow. To the left, it's an arrow. Up is an arrow. Down is an arrow. But into or out of the page is a dot or an X. So an X if it's going away from you, and a dot if it's going towards you. Because it's meant to resemble an arrow. So if an arrow is coming at you, you see the point, that would be the dot. If an arrow is moving away from you, you see the feathers on the back, and they make a sort of X pattern as it's moving away from you. So let's look at this first example. Positive charge moves from the top of the page to the bottom. So the velocity of our positive charge, this little V, is pointing down, and it's positive. That's why I put a plus sign there. Positive charge moves from the top of the page to the bottom of the page. If it experiences a force pushing it towards the left, so the force goes left, which way does the external magnetic field point? So how would you figure this out? Your thumb would point in the direction of the velocity vector. So your thumb would go down. So maybe I can write all that out. So our thumb points down. All right. What else? The force is the palm of your hand. So the palm of your hand points. Which way is the palm of our hand going to point? So the thumb is down. It goes, palm of the hand is the force. It points left. Whoops. So which way does your, which way do your fingers? Okay, apparently I've got some sort of wacky formatting going on, which I don't understand. But I think I'll try to change it. I don't think we want those words as a superscript. Okay. Well, this has just been an adventure. I just have all kinds of formatting issues, don't I? All right, let's see if we can straighten this out then. So your thumb points down because of the velocity vector. The palm of your hand points left. So this is all on the right hand. Thumb is down, palm goes left. The only way that the thumb can go down and the palm can go left is if the fingers are pointing towards you. They point towards you. And remember, we've only got, so that would towards you, and that would be out of the page. So that would be out of the page. All right, we'll do it in class, I promise. Let's see if we can look at this one. So we have the B field, we've got X's, and that means it's pointing away from us. So your fingers Your fingers point into the paper. That's the B field. What else do we know? So the charge moves up. That means your thumb points up. So your thumb points to the top of the page, your fingers are into the page, and that means that the palm on your right hand is pointing left. And that would be the direction of force. All right, again, I promise we'll do this in class and it hopefully won't be so awkward. There is a video on auroras. I will post the link on the Canvas assignment. We should be in good shape. All righty, let's talk about magnetic field due to a straight wire. So if you have a straight wire, if the magnetic field is coming, if the positive current is coming towards you, your fingers will curl in a counterclockwise direction. If it goes away from you, they curl in a clockwise direction. So remember, X is away from you. So if it's away from us, it is clockwise. So this top one would be clockwise, and the bottom diagram would be counterclockwise. Top one would be clockwise, bottom one would be counterclockwise. There is an equation that relates the strength of the magnetic field to the current and to how far away you are from it. You don't need to memorize this equation. You don't need to memorize it. You've had two to remember, and this was not one of them. So what's the force between two parallel wires? So if the current is posted in the same direction, in this situation, we've got the current with X's, so it's going away from us into the paper. If you put your right hand on the one on the right and have it going into the paper, it makes it curl in a clockwise direction. If you come over here and again, it's into the paper, it curls in a clockwise direction. So you can see that in the space between them, they're pointing in opposite directions. This one's coming from the top down and the one on the right is coming from the bottom up. And opposites attract. And so when the current is in the same direction, the two wires will attract each other. When the current is in opposite directions, they're going to repel each other. And you could draw your field lines around it. And again, we'll work with this in class. Let's talk about magnets and solenoids. So you can take a wire and put a current through it, and that creates a magnetic field around the wire. If the wire is shaped into a loop, we call it a solenoid. And if we have the loop go all the way around and we use the right-hand rule and we trace the direction of the current, that's the little blue arrow, and indicate the magnetic field around the wire, that's the little red arrow, you would see that in the open space in the center of the wire, the magnetic field lines all point in the same direction. So if you make a loop of wire, you have a lot of little magnetic field lines pointing in the same direction in the middle of the loop. And that leads us to the capability of being able to make electromagnets. If you take a piece of iron in the middle of all of that, it'll reorient the magnetic domains in the iron and you'll make your electromagnet even stronger. You don't need to remember the left-hand rule. It was just a way to show you which way the North Pole and the solenoid is going to point, but I'm not going to ask you that. So if you take a metal of some sort, a bolt of some sort that has ferromagnetic atoms in it, so it has usually some kind of iron in it, and you wrap wire around it lots and lots of times, and you can connect it to a battery to put current in the wire. What you can do is create an electromagnet, and you are able then to pick up paper clips or things of that nature. I have been off and on not so successful doing this in lab. We may try it, we may not. But there's lots of stuff on the internet. All righty, so to increase the strength of your electromagnet, you would increase the number of coils, the number of loops of wire. You could increase the current through the coils, or you could do both of those things. So one or the other or both will increase the strength of your electromagnet. Why would we want an electromagnet? Well, we'd like to be able to control the magnetic capabilities. If you look at these things, depending on what your core is made out of, it's made out of something called soft iron. It's really easy to reorient the magnetic domains. And so you can make it magnetic, but when you turn off the current, the domains migrate back to a more disorganized state, and the electromagnet loses strength and drops whatever you've picked up with it. If you have hard iron, once you reorient those domains, they're more or less fixed in position. And so you would probably use hard iron if you're trying to make permanent magnets, and soft iron if you want to make an electromagnet. We've used solenoids in all kinds of things. Just there's a variety of applications for things that have magnetic properties that can be controlled, turned on and off. So I think we'll stop with this. Go back to the Canvas page and be sure to watch the video on the aurora.